The previous topic we talk about the filtration, and now we will consider the centrifugation. Both centrifugation and filtration, the operation is the same. We would like to separate solid from the solid liquid mixture, aside from the solid liquid mixture. But the centrifuge we use to separate material that different density. Aside density, we use force that's greater than gravity. We use the force that's greater than velocity. The centrifuge is used to remove cell from fermentation broth, eliminate cell debris. That cell debris means very small cell particle obtained from the cell disruption or homogenization. That the cell disruption or homogenization we talk to you for the next topic. Okay, for this case, we use to remove cell, remove cell debris, also to collect the precipitate. Precipitate is also the solid that's obtained from the precipitation. That we will talk to you for the next 3 or 4 weeks about the precipitation. Okay, for precipitate, and also we use to prepare fermentation media, such as the clarification of molasses to produce the wort for breathing, something like that. This is the application of centrifugation. But when you compare to the equipment between filtration and centrifugation is more expensive than filtration. But it's also effective when the particle is very small and difficult to filter. There are some disadvantage and advantage. The expensive in the cost, but effective for very small particle. And also centrifuge can produce the thick concentrate salad, or cream containing more liquid in filter case. And also some disadvantage for centrifuge is generate large amount of heat because these are due to the friction. Okay, for the operation of the centrifugation, we have to need the good ventilation and cooling. The cooling system in the equipment to reduce the heat, to reduce the temperature, and also the ventilation. When you are engineer, you have to cooperate with the auto engineer, civil engineer, mechanical engineer in the industry or the plant, work together to design the ventilation. I'm not sure you know about the ventilation. Pilom, did you know about the ventilation like this too?
No, I don't.
Okay. Pondakan, you know about the ventilation?
Excuse me?
What is the ventilation? You
Like
know about this?
To transport air to other place.
Okay. That's correct. We have to thank you for the answer. That's correct, because we would like to control the quality of air in the equipment. That's why we have to exchange the air in the system and out of the system. Ventilation, that means to design the system with the airflow, good airflow between the system and surrounding. That's why the flow of air is good. We control that's like the temperature, something like this. Also, the ventilation is the airflow. It's like in and out the system. You have to control the flow, and also you have to, if your clean room, airflow in should be sterile. That's right, to be sterile before to flow. Okay, this is the ventilation. You can use the design of ventilation. Good design of ventilation can help the control the heat in the system. Okay. And also the centrifugation is more effective when the particle large and also the liquid velocity is low. The density difference is great, or the high difference in the density difference. If the density is small or low value, it's difficult to centrifuge. It's difficult to centrifuge. But if you compare between the size of the equipment, small size and large size, that's right. When the size is increased, the capacity is not increased. That's right for that case. The increasing by the size it's not impact the increasing of the capacity. Okay, for this case, it's very important. When you scale up of the centrifuge, when the size is increased, the speed of the centrifuge should be lower than the small size. This is the most common one for the scale up. Okay, did it show you the general operation of the centrifuge? For this case, if we have like the cylinder, something cylinder or the tube, that's why we have some rotating. That's right. We rotate the solid and liquid mixture. And liquid mixture, we feed the liquid mixture and solid mixture at the bottom. That's right. When you rotate, R1 is the radius of the liquid surface. That's right. R1 is the liquid surface. When you rotate, some liquid that solid is moved to the wall. That's right. Moved to the wall. Okay, and R2 is the wall. That's right. Radius of the wall. And we consider in when you rotate the system, some liquid is moved to the wall, and also the solid is moved to contact the wall. That's right, to contact the wall. For that case, you can collect the solid is on the surface of the wall. That's right, and sometimes it's due to the gravity force, also will setting down. You can collect the liquid and solid by the centrifugation. It is due to the centrifugation force. And another example is the common one used in bioprocess. We call this disc bowl. That's right. We have some is it 2 dimension? Is it the disc? We can rotate this. That's right. We can rotate this. And if you feed the solid and liquid mixture, and also this rotating. That's right, rotating. And some solid will accumulate at the outer side, and you can collect the solid by throw out. That's right. You use some for this is some this stack bowl certification. This stack bowl certification. I think we have some example. The configure will show you in the video. Either tubular or this stack bowl. This is this stack bowl centrifugation. Right. We rotate continually. That's when you feed the liquid and solid. Most solid will move to contact with the wall, outside wall. That's right, outside wall for this case. Okay, these are the operation of this stack bowl. Okay. And then you can separate liquid and solid. You can separate liquid and solid. And the next example we call like this is this stack bowl. That's like the same, but you look at this also. For this case is more clearly defined. There's some we feed liquid that's that or of the solid will accumulate on the surface, and then you can remove the solid out of the system. For this case, we remove in this and you feed like this. This is the practical one. We have the big size of the centrifuge at pilot plant. As at pilot plant, we have for this case we operate both centrifugation and filtration. We have the centrifuge. The solid will accumulate on the surface of this. Surface of this. But in this wall, we have some the filter. That's right, filter phase or the screen. We have the hole. That's right, we have the hole for the phase. And solid, for example, like this. I'll show you. Okay. This is like the solid. It is also the hole. That's right. the solid will accumulate on the surface. And liquid is flow across the filter. This is the liquid. That's right. This is the solid. We call it turbo centrifuge. We heard very high force or very high force. That's right. Very high speed, force and speed. That means we rotate like this, or the solid will accumulate on the surface, and the liquid pass through the filter or the hole. That's why we call it the turbo centrifuge seat. That's right. This is both centrifugation and filtration. And filtration also. That's right. We operate both technique, centrifuge part filtration. This is show you in the pilot plant. I think the next year you bring you to visit the pilot plant. Okay, this is the common one we have in the pilot plant. This is the big one. That's right, the very big equipment. Okay, this is also use the centrifuge operation together with the filtration. We can use it to separate solid, that's right, and liquid. Okay. For that case, you will collect the liquid, you send to the next step, and solid will go to the next step. Okay, the next one we introduce you about the theory that talk about the centrifugation. Because centrifugation, as I talked to you previously, we have some solid that have liquid surface. This is a solid, and also the solid will setting down. That's right, setting down. And also we'll talk about the particle flow in the liquid due to the gravity setting. That's right, gravity setting. If the dilution system is the amount of liquid is low value compared to the amount of solid is low value compared to the liquid dilute system or dilute suspension. Okay, we can calculate the sedimentation velocity. Sedimentation velocity is the velocity that the solid will setting down to the bottom. Okay, for this case, we can apply to the centrifugation force. We can apply for the centrifugation force because this is we operate based on omega. That's right, based on omega. Omega means the angular velocity. That's right, angular velocity or rotation speed. That's right, or rotation speed of the ball. But mostly we compare between G and omega. That's right, for G and omega. For the centrifuge, the omega is very high compared to G. That's right, compared to G. Okay, for the centrifuge, we apply this equation. UC is the particle velocity in the centrifuge. But for this, when the particle setting due to the gravity, due to the gravity. Okay. Everything is the same except this term. This is gravity. For centrifuge, is omega. R is the radius of the centrifuge. That's right. Radius of the centrifuge. Only when we calculate the centrifuge effect, we use the G number or the term of sigma. That's right, the term of sigma. How many force that you act on the centrifuge? Mostly we operate at Z is greater than 300 to 16,000. That's right. What does it mean? This is the 300 higher than G force. It's very, very high. That's right. It's very, very high. But if you operate in the small laboratory, this is in the industrial scale. If you operate in laboratory, the set value is very high compared to the industrial. That's right. You can operate at very high set force compared to the industrial scale. Okay, that if you increase the size, the set factor should be decreased. But you cannot operate at very high speed for the bigger size. Right. It's difficult to do that. Okay, this is we talk about the sedimentation will occur in the centrifuge. That's right. That means the particle will move away from the center. That's right, from the center to the wall of the ball. If you increase the velocity of motion, also we will increase the rate of sedimentation. Okay, the particle velocity will increase by centrifugal speed. That's right. For this case, we consider based on this equation. Velocity will increase with the speed increase. Diameter increase, the density difference increase, and decrease of viscosity. We have 1, 2, 3, 4. If you increase the density difference, okay, you can increase the velocity. That's right. If you increase the diameter, increase the velocity. If you increase the speed, increase the diameter, and then you reduce the viscosity of the fluid and solid or substance, you will increase the velocity. It is the technique to improve your centrifugation. That's right. And also, I talked to in-batch and continuous. Mostly in batch, we can operate with higher support, but in industrial or continuous process, we operate with lower. That's right, with lower. For the batch, that's why we increase the running, we increase by increase the equipment. That's right. And also the continuous flow, we can use the increase by decreasing the feed flow rate. That's right, the feed flow rate. Okay, for the scale up of the centrifuge from the lower scale to the higher scale, or from the smaller to the bigger one. That's why we use the sigma parameter. We use this sigma. Sigma parameter is the flow rate divided by the UG. That's right. With the volumetric flow rate or feed rate divided by the terminal velocity or UG. And then you can compare between the centrifuge of smaller size with a bigger size. If we consider one is smaller, right? 2 is larger. Okay, you can compare the ratio of the Q and sigma. Q is the volumetric flow rate of the feed. Sigma is Q over UG. That's right. Q1 over sigma 1 equal to Q2 over sigma 2. We can use this relationship to scale up. That's right, to scale up. Okay, I think we have this example to show you how to scale up or how to calculate the flow rate for the higher or the bigger, for example. Okay, the bacteria cell from fermentation growth are recovered by using pilot plant scale tuberable centrifuge. As the cell approximately is spherical. This is the sphere, the morphology of the cell. The radius of the centrifuge is 0.5 micrometer. Unless this is the radius of cell. That's right. This is the diameter of particle or the cell. And the density of particle is 1.1 gram per cubic centimeter. And the diameter of the ball is 10 centimeter or I equal to 5. That's right. Ball length, this is the length or the height of the ball is 100 centimeter. And diameter of the outer opening of the ball is 4 centimeter. This is the center. That's right. Okay, this is 4. This is 5. That's right. Okay, this is the liquid surface. And this is the wall of the ball. It's 10 centimeter in diameter or 5 in radius. For this case, we operate the centrifuge at low rotation speed of 5,000 RPM. Omega equal to 5,000, not omega, but instead we call this N. 5,000 RPM. That's why if we show in terms of omega, omega should be radius. That's right. Per time. Mostly we have to convert radius to RPM. That's right. 1 radius, 2 radius. You know is a trigonometric 1 radius or 2 radius. Okay. The question is determine the flow rate of fermentation flow that can be attained. Okay. For this case, we record the sigma factor. Sigma equal to Q over UG, which is equal to omega square V divided by 2G of R2 divided by R1. That's R1 is the outer surface of the liquid, and R2 is the radius of the blow. That's right. And also, we can express the distance. Okay, for this equation, I show you in the book that I wrote in the Google Classroom. You can look at this to why we get this equation. That's right, we get this equation, and also UG calculate from this equation. That's right. Okay, for this example, we assume the viscosity is water and density of the water. This is the viscosity and density of suspension. This is for suspension, not solid. That's right. The solid we know already in the problem statement. This is the solid. Okay, the first one you have to calculate UG. That's right. You calculate UG. You know the density of particle, the density of fluid. That's right. Diameter of particle, and gravity. And also you convert the unit from cubic meter to cubic centimeter to cubic meter. That's right. And then divide this by viscosity. You get UG in this term. This is UG. And then you calculate the sigma factor. Sigma factor, you know omega. That's right. But you have to convert omega in terms of the revolution or per minute. This is n. That's right. But you know, one revolution equal to 2 pi radius, because this is 2 pi. That's right. This is pi over 2. That's right. This is a 2 pi. 2 radius is one round. That's right. 1 round is 2 pi radius. Okay. You know that this is the radius equal to 2 pi radius. Okay. This is the omega. You have to convert the unit of omega. That's right. Omega to n. You convert omega to n. That's right. The one revolution equal to 2 pi radius. And multiply pi. Pi unit is radius. And also R2 minus R1 for this square. This is R2, this is R1. G, that's right, R2, R1, this is the unit converter. That's right, 1 meter equal to 100 centimeter. 1 meter equal to 60 seconds. And then you know the sigma factor. You know the sigma factor equal to Q over UG. That's right. You know sigma factor, you know UG, you can calculate Q. Q is the fit for it. Okay, for this case, we use the fit for it is 0.66 liter per minute. That's right, liter per minute. Okay, and also we can use this for the scale up. I will give you an add homework for the scale up. For the case, you use the data from the lab scale. And then you use the lab scale data to estimate the bigger scale or the larger scale. That the same technique that I talked to you in the filtration. Is I talked to you about the centrifugation in conclusion. That's right. And also you can study in the unit operation in more detail of this technique. How about the centrifugation? How about the filtration? Okay. I talked to you only the application of the centrifuge for the bioseparation in this class. Okay. This is the topic. It is finished for